Recording in progress.
Okay, so this is CodeTON Round 5, and we're going to discuss the first 4 problems, A to D. Let's get started with problem A. So in this problem, there are 2 players playing. Let's say player A and player B, and they have a bunch of monsters with different points. So 5, 2, 3, 10, 1, 4, 5, 10, 1, 7, 2. And the players will take turns. At first, player A will go, then player B will go, then player A, and so on. And at one player's turn, he can pick one monster from his side and one monster from the other side. And here is what's going to happen. Let's say the first monster is of value 5 or value X, and the second monster is of health or value Y. So the first monster's health is going to become X minus Y, and the second monster's health is going to become Y minus X. I think this is correctly. So let's take a look at what happens. So the first monster's health is going to become 5 minus 1, which is 4. And the second monster's health is going to become 1 minus 4. Sorry, 1 minus 5. This is minus 4. And if some monster's health becomes negative or 0, then we'll consider that monster dead. So we'll just consider this as 0. So this is what's gonna happen. Let's take a look at another example. Let's say the health of the first monster is smaller. So let's say 2 and 8. Then the first monster's health is going to become 2 minus 8 minus 6, and second monster's health is going to become 8 minus 2, which is 6. And you can consider this minus 6 as 0. So this is what's happening. The health of both these monsters is being decreased by the smaller health. So 2 becomes 0, which is 2 is being decreased by 2, and 8 becomes 6, which is also 8 is decreased by 2. And here the same thing is happening as well. The healths are becoming decreased by the smaller amount. So 5 minus 1, 4, and 1 minus 1 is 0. So this is how we can take a look at the operation. So this tells us that at each step, the health of whatever monster we pick, it doesn't matter. The health of these two monsters is being decreased by the same amount. And if the healths are being decreased by the same amount, then which person is going to win? Obviously, the person with the greater sum of values is going to win. So for example, if this person had a sum of 20 and this person had a sum of 15, so this person is going to run out sooner with the smaller amount of sum. So the person who has the greater amount of sum of all the values is going to win. If they both have the same amount of sum, then it is going to be a draw. So then then we need to output according to the statement, the name of the two players or a draw. So any confusions in this problem? No, someone said no. And so let's take a look at the code then. And can anyone confirm if you can see my cursor or not? Is my cursor visible on the screen?
Yes.
Okay. So here at first we're taking the size of the two arrays, and then we're taking the two arrays in input, and then we're going to calculate the sum of the two arrays. Here I use the accumulate function, or you can just normally sum up the values in the loop, and if we're going to output according to the sum which is greater, and if they are equal, we're just going to output draw. So any confusions? Or if any one of you had a different approach to it, you can also discuss that. Okay, so let's move to the next problem then. So I like this problem. So this is problem B, and the problem says that we have 3 stacks of books, and each stack has n books. Each of the 3 stacks has n books. Audio lag. So is my audio lagging? Is it lagging to everyone else? Okay. So I think your internet is bad, I guess. Okay. So now we have problem B. Okay, so we have 3 stacks of n books. Let's say n is 5. So we have 3 stacks of 5 books. Yeah, and all these books have a different number. So let's say these are the numbers from the books, and so on. And we are also given a value x. And what we have to do is we have to take some books from the top of the first stack, some books from the top of the second stack, some books from the top of the third stack, and we have to figure out if by doing this process we can get the value x by bitwise ORing all those values. So if we take these values, 5 bitwise OR 2.
Can you mute everybody? So there is a disturbance. Can you mute it?
Yeah, okay, I'll just mute. Okay, yeah. So what we have to figure out is as we pick these books, if the bitwise OR of these books can become equal to x or not. So we're going to take the top books from each of the stacks, some amount of books from the top of each of the stacks, and we have to make the bitwise OR of all these values equal to x. We just have to print if it is possible or not. So when we're dealing with problems which involve bitwise operations, it is always best to look at the problems using bitwise representations of the numbers. So let's take the bitwise representations. At first, let's take a look at the bitwise representation of x. Let's say x is equal to 10. Then the bitwise representation will be 1, 0, 1, 0. And let's say another value is 1. So what will we get if we OR these two values together? If there are any 1 in any of the bits, it will become 1. So for all the bits of x where we have a 0, we cannot ever get a 1 from any other number. If we get at least 1 for any of those bits where x has a 0, then the bitwise OR will not remain equal to x. Sorry. So I'll repeat again. Let's say this is x. So we cannot take any value from the stacks which has a 1 bit in place of any of the 0 bits in x. So if this was x, we cannot take any values which has a 1 in any of these places where x has zeros. So we cannot do that. So for all of the stacks, let's find the first place from the top which has such a bit. So for all the 3 stacks, we're going to find the first place where there is a 1 in some index where x has a 0 in that bit. So if x was 10, so x was 10, and if this number was, let's say, 1, then in the first bit, x has 0 and 1 has 1. So this is the first index, first such index. So we're going to find that. So we cannot take any elements from this part of the first step. So for all the steps, we're going to find such indices. So let's say these are such the indices. So we cannot take any of these values or these values or these values, because taking them will make a bit 1 where x has a 0. So we cannot do that. What we can do is we can take a prefix of these numbers, a prefix of these numbers, and a prefix of these numbers. By prefix, I mean a top portion of these values. But it turns out that it is beneficial for us to take all of these values. So all of these values, because we have eliminated all the values which can turn any 0 into a 1. So all the 0 bits that we have in x will remain 0 by taking the bitwise OR of these elements. But we want to make all the ones that we have in x, and so we want to take all these values and make their OR so that we get 1 in these places. So it is beneficial for us to take as many elements as we can to make ones in these positions. So this is the main idea of this problem. So is this clear, or should I go over the idea one more time?
No, once more.
Sorry? Repeat. Okay. So just to know you guys' thoughts, some of you got it right. So you can write it in the chat if you got it or not. I'll repeat it one more time, but if any one of you understood, you can just write it in the chat. So in our problem, we can take a prefix of the first step. We can take a prefix of the second step. We can take a prefix of the third step, and bitwise OR all of these values, and we want to get the value x. So to get x, we cannot get a 1 in place in any of the bits where x has a 0. Is this understandable? So we cannot take any elements which has a 1 in any of the bits where x contains a 0. Is this understandable?
Yes, yes.
Okay. So we cannot do that. So that is why we're going to find out the first index from the top, which contains one such bit where the bit is 1, where x contains that bit as 0. So if x was 10, again, for example, and if one such number was 1, here in the first bit, in this bit, x contains 0 and this bit contains 1. So if we take this number in the bitwise OR, then this bit will be turned on. But in x, this bit is not turned on. So we cannot take this, and if we cannot take this element, we cannot take any elements to the bottom of it. So we're going to find first such indices from all the 3 steps, and we're going to eliminate all those values. And after we're done eliminating all those values, we have some elements left from the steps. And we know if we OR these values, we'll never get a 1 in place of a 0. We'll never get a 1 where x contains a 0. So all these bits will be fixed. All these bits will be 0. We just want to make all the 1s to the bits where x contains a 1. And to do that, we're going to take all these values, and that is going to increase our chances of getting 1 in all these places. So is it clear now? Yeah, anyone else has any confusions? So yeah, let's go to the code now. So in the code here, we're taking n and x in input. So we're taking an array like this. So 3 by n. So we'll take the array in input. Then for all the 3 arrays, so here I'm running a loop for the 3 arrays, and this is the total variable. This will hold the bitwise OR of all the values. So this will hold the bitwise OR of all these values, all the green values. So, and for each of the stacks, we do not actually need this. So for each of the stacks, we're going through all the elements from top to bottom. And if at some point, okay, so if at some point the prefix OR of all the values ORed with x is not equal to x. So what this means is, if x is 10 and we get another element, let's say 4, where the new number contains a 1 where x contains a 0, then the bitwise OR of these two values will not be equal to x, because we'll get a new bit here. But if the new element didn't contain such a bit, so if the new element was this, so it doesn't contain a 1 where x contains a 0, then the bitwise OR of it will be equal to x. So this is equal to x. So that is what we're checking. If now OR x is not equal to x, so that is when we have a new bit where we had a 0 bit in x. So then we're going to break out. Otherwise, we're going to OR this value with the total variable. So after we're done with all these three steps, we're just going to check if the total variable, so the bitwise OR of all the values, is equal to x or not. Then we can print yes or no. So yeah, any confusions with the implementation? Okay, great. So let's move to the next problem. So this is problem C. How many questions will you discuss? I'll discuss 4 problems, the first 4 problems. So in this problem, we have n balls. So we have an array of n balls. So the balls are numbered from 1 to n. So let's say the balls are like this: 5, 2, 5. Let's say the balls are like this, and we can do some number of operations. In one operation, we can pick 2 indices, I and j, where I and j are different, and both these indices have the same ball, same colored ball. So we can pick, let's say, these 2 indices. These 2 indices are different, and these 2 have the same colored ball, and we can get rid of all these balls from index I to index j. So by doing this operation 1 or more times, we have to figure out the maximum number of balls that we can remove from the array. This is the problem. So I use dynamic programming to solve this problem. So we're going to at first take a look at a slower dynamic programming approach, then we're going to optimize it. So let DPI denote the number of ways or the maximum number of balls that we can remove from the first I balls. So this is max number of balls we can remove from the first eyeballs. So if we only consider the first eyeballs, what is the maximum number of balls that we can remove? So obviously the answer for the problem will be dp of n. This is the answer. And let's take a look at the transitions. So let's say we're in index I. So one candidate for dp of I is going to be dp of I minus 1. So this is one candidate for dp of I. And so this is going to be if we do not make any operations here. But if we make some operations from this index, then the color of this ball will matter. So the color of this ball is 5. So we can pick any such ranges from 5 to 5 and remove this. Let's take some more elements. So we can also take this range and delete all this. So then what is going to be the transition? So for all j where array of j equals array of I, we're going to maximize DPI. So DPI will be max of DPI, and we're going to, let's say this is j. So we're going to remove all these balls from j to I. So we remove all the balls from j to I. We're removing I minus j plus 1 number of balls, and now this was the number of balls from the previous index of j. So this is what our transition is going to look like. So to calculate DPI, we're going to go to all the j where array of j is equal to array of I, and we're going to use this. We're going to remove this number of balls, and we're going to add dp of j minus 1 to it, and we're going to get the maximum value of DPI from it. So can anyone tell me what is the time complexity of this approach, of this dynamic programming approach?
N square.
Yeah, yes, this is going to be open square. Just consider an array where all the elements are same. So let's say all the elements are 1. So to find the dp value of one index, we need to consider all the indices before it. So that way the complexity will become O of n square. But there is a way to optimize it. Let's see how we can optimize it. We just need to modify the equation a little bit. So we need the maximum value of this. So this can be modified like I minus a minus 1 plus. So we can do this. So we need the maximum value of this. And as I is fixed, I is the current index, then we just need the maximum value of this for all the j where array of j equal to array of I. So we can keep another array where for all the colors I kept an array called mx, I think mx or something like that. So I kept another array. So where, okay, first we just need the maximum value of this for some color. So if we're at this index, we just need the maximum value of this for the color 5. So if we kept all the if we kept track of the maximum value for all these indices which contains 5 in some array, then we can just take a look at that and we can do I plus that to get the maximum value of this. So I kept another array. So in that array mx of 5 will contain the maximum value of this j minus j minus 1 plus dp of j minus 1, and for all the 5s will contain the maximum value of that in the mx array. And when we're at this index, we can just do dp of I equal to max of dp of a minus 1, but this is the first case, and we'll do I plus mx of array of I. So now this becomes our transition. So for one index, we just need to calculate this, and we just need to update
Hello?
the value of mx. Yeah, hello.
It would be I plus or I minus.
Here we need I minus, because if you take this minus as common, so then we'll get j minus 1.
No, at the last
Or
step.
do you mean here? Yeah.
Yes.
Okay. So here we will have plus because we're taking the maximum value of this. So this is actually I plus minus of j minus 1 plus dp of j minus 1, right? And
Okay.
as we're keeping track of the max value of this, we just need I plus this value.
Okay.
Okay. So now this approach will become often. So any confusions or any doubts about the approach?
So first we have to
I think
pre-compute
someone
the
unmuted,
MX part.
but I'm not hearing.
Hello?
We don't have to compute. We can just update the values as we go along the array. So let's say we computed dp of I for the ith index. Hello. Hello everyone. Am I audible?
Yes.
I'm having a little bit of internet issues. Is my screen visible now?
Yes.
Okay, so can you explain again the initial? Yeah. So I'll explain the approach one more time. Let's erase all of this. So dpi will denote the maximum number of balls that we can remove if we consider only the first I indices. Did you understand up to here? The person who had the confusion. Okay. So for dp of I, if we do not, let's say the I'll erase all of this. You have the confusion. Yeah. So let's say the ith index is this index, and at this index we can make an operation to remove some amount of balls and we cannot make an operation. So there are two choices to us. And someone said to give an example. Yeah, this is an example. So there are two choices. We can remove this part or not remove. If we choose to not remove, then dpi is equal to dp of I minus 1. So if we do not remove, the maximum number of balls that we can remove from the first I indices is just the maximum number of balls that we can remove from the first I minus 1 indices. So if we choose to remove, then we can remove one such subarray, or we can remove this subarray, or we can remove this subarray. So we can remove a subarray where both the values are 5. As we fix this index I, so we just need to find another index j. Let's call that index j, which is less than I, and array of j will be equal to 5. So for all the j, where array of j will be equal to array of I, the transition is going to be like this. dp of I will be max of dpi, and we can remove all these values in the middle from j to I. So we're going to remove I minus j plus 1 balls, and if you remove all these balls, so we removed all these balls, then what else do we need to consider? We just need to consider the maximum number of balls that we can remove considering all these indices. So dp of j minus 1 plus dp of j minus 1. So understood up to here? Any confusions?
This part I got, but how you are computing the mx part, I am not getting how you are doing that.
Okay. So you understood the simplification, right?
Yes.
Okay. So as we go along the array, so for this 5, we need to know the maximum value of minus 1 plus dp of. So for this 5, we need to know the maximum value of these for all these 5s, right?
Yes.
So we just need to know the value for all the 5s which are before this 5, right?
Yes.
So let's say when we calculated the dp values for these indices, then we updated the mx5 value with the maximum value of that. So when we when we are calculating this index, then we can update mx5 with the j. So if we were here, then we would maximize mx5 with, so if we were at this index, so we would maximize with this value dp of I minus 1. So for this index, we'd maximize with this value, and when we were at this index, we'd again maximize with this. So for this 5, I'll erase some of this. So for this 5, let's say this is index 2, then we will maximize with the value minus the index of this is 2, so we'll get 2 minus 1 plus dp of 2 minus 1. So for this 5, we will maximize mx5 with this. For this index 4, we will maximize with minus 4 minus 1 plus dp of 4 minus 1. Is this understandable now?
Yes, got it.
Yeah, so as we go along the array, we can just keep updating the mx array, and when we come to this index, we can check that mx array to find the maximum value. So I think if we take a look at the code one more time, this is going to be a lot more clearer. So as you can see, the code is really small, like 6 or 7 lines. So here I'm taking the array in input. I'm taking n in input, and I'll take the array in input here. I use 1 based indexing here. So from 1 to n, I'm taking input in the array. And I also have 2 more arrays, the mx array, to keep the maximum value of such values. And I also have the dp array. And at first, the maximum value of all the colors, we don't have anything. So I'll just store negative infinity in all those indexes. And initially dp of 0 is 0. So now when we're calculating dp of I is going to be max of dp I minus 1 and I plus mx of array I, as I said. And then we can also update mx of array I. So I'll update mx of array I using dp of I minus 1 minus I minus 1. This is just it. And then we can finally print out dp of n. How to know the transition step in any dp problem? So you have to be habituated in solving dp problems. So you have to solve a lot of problems to easily understand the states. And someone said, give some tips on that, sir. So on which do you want tips in? dp. Oh, as I said, you have to solve a lot of dp problems to know about this little optimization. So this is a pretty common optimization, separating the I and j parts. And which problems? Yeah, you can practice from code forces. My normal routine is to practice from code forces. I don't usually solve from other places, but I'll occasionally do some contests or marathons like that. You are never checking if array I equal to array, because we are not running a loop here. We're checking the value of mx array I. So in mx of array I, we'll just include all the values for array of I. So we don't ever need to do that. I'll give an example here. So let me just erase this. So for this 5, we just need to know the maximum value for these 3 5s. And but when we are at these 5s, we upgrade the mx5. We updated mx5 with their corresponding values of minus j minus 1 plus dp of j minus 1. So mx of 5 already contains those values. So we don't need to check those values again. When we're at this index, we just need to take a look at mx of 5. That is it. How much time did it take for you to strike this DPID? It didn't really take me a lot of time, but it is because I solved similar problems like this before. So it was about like 6 or 7 minutes. So any doubts about this problem? All clear. Okay, so let's move to the next problem. So this is problem B. I do not like this problem. This is one of those frustrating problems, but we have to solve them, right? So in this problem, we have a process. So some guy has n friends. So the n friends or n animals are numbered from 1 to n. 1, 2, 3, 4. Let's say n is 6. So sorry. So he has friends from 1 to n, and he is going to play with a subset of these friends some number of times. So at each step, he's going to take a subset of these friends. So let's say 1, 3, 5, 6. This is a subset, and he can play with these friends. But there is a limitation. So there are some restrictions. He always has to take friend 1. He cannot ever take friend n. And there are some other restrictions. So there are m other restrictions, and the restrictions are like this: ui, vi, and yi. So we're given a bunch of u, v, and y. And what this tells us that this took me a little time to figure out. So if there are some amount of times, let's say for x times where u was present in a subset but v wasn't, so u was present in the subset but v wasn't, and for y amount of time u was not present in the subset but v was, so x plus y needs to be less or equal to, let's take this as z, x plus z needs to be less or equal to this y. So there are m conditions like this, m restrictions like this. So we need to follow all these restrictions, and we need to figure out the maximum amount of time that this guy can play. So he can take a subset and he will pick a time, let's say 5. So he will play for 5 minutes with this subset, but he will have to maintain these restrictions. So I'll clear about the restrictions one more time. If there is a restriction of u, v, and y, so let's call x the amount of time that the guy played with u where he didn't play with v, and y or z the amount of time where he didn't play with u but he did play with v. So x plus z needs to be less than or equal to y for all the m restrictions. And following all the restrictions, we need to figure out the maximum amount of time that the guy can play, or if it is an infinite amount of time, then we need to also output that. So yeah, understanding the statement is a task itself. So let's take a look at the approach now. So if some problem has something to do with pairs like this, u and v, most likely the problem is most likely the problem has something to do with a graph. So take a look at graph, think about graphs that might come in handy. And for our case, that is what we're going to do. Let's take a look at the m restrictions. Let's say the restrictions are like this. Let's say n is equal to 6. So these are the u and v values, and we made an edge between all the u and v, and the value of this edge will be equal to y. So we made a graph from all these m restrictions. So we have some weights of these edges. Okay, so there are two main cases. 1 and n are in the same component, and 1 and n are not in the same component. Let's take a look at the second case first. If they are not in the same component, then what we can do is we can take this component. So this will fulfill the first two conditions. We're taking the first animal, and we're not taking the nth animal. This is fulfilling the first two conditions. And for the other conditions where there is a restriction on u, v, and y, such restriction will only affect us when we're taking a subset, okay, let's say we take this subset 1, 2, and 3. So here we're taking 2 and we're not taking 4. So this is one such case where we're taking one element and we're not taking another element from one such restriction. And here this time will add up. So we cannot do this for more than one time. If this was, let's say, 5, we cannot do this for more than 5 times. But if we do not cross any edges like this, so if inside our subset, so if this is the whole subset, we are not crossing any edges like this, and if we do not cross any edge, then we are not bothering. We are not, let's say, what can we say? We're not disobeying any such restrictions. So if we take a whole component like this, we're obeying all the restrictions. So if this is such a case where 1 and n are not in the same component, then we're obeying the first 2 restrictions, and we're also obeying all the m restrictions. So this, we can do this forever. We can keep doing this forever. So for the case when 1 and n are not on the same component, then the answer for that will be infinity. So is this understandable up to here? So the case for when the answer is infinity, is this understandable? Any doubts up to here? Five and 6 can be used in output. They can be used in output, but we are not going to use them, because if we just take this subset, we can keep taking them forever without disobeying any of the restrictions. Repeat once again, how did you make a graph? So we have m restrictions. So if we have m restrictions in the form u, v, and y, for u, v are 2 animals and y is a value. So we can take these values and we can make a graph where we're going to add an edge between nodes u and p with a value of y. So if uv was like this, so we would add an edge between 1 and 3. So this edge, and the cost of this would be 2. So this is how we made a graph from all the restrictions. And if we take a subset like this, so if we take a subset like this, where we're cutting through some edge, then that is when we're going to run into problems, because in that case we're taking some element into the subset and we're not taking another element from that restriction into the subset. So we can do that at most y times. But if we do not do that, we can keep doing this forever. We can keep taking this subset forever. So that is when we're going to output infinity. So if this is the case when 1 and n are not in the same component, then we can output infinity. Now let's take a look at the case for when
forever, because if we traverse it, it means that the time should be decreased. Sorry, increased. And it should
which
be
time?
5. Like if 1 and 3 are disconnected from 2 and 4, so we are saying that the step could be repeated up to infinity. But
Yes.
there is a restriction on 2 and 4. If we keep doing that, won't it reach a time limit?
No, the restriction is when we're taking 4 and not taking 2, or we're taking 2 and not taking 4. The restriction will apply then. But if we take both of these values, then the restriction won't apply.
Okay, understood.
Okay. Yeah. So look at the case when 1 and n are in the same component. I'll erase the unnecessary stuff here. So let's say n is equal to 5. I'll erase all this here. Okay, so n is equal to 5. So this is 1 and this is n. And 1 and n are in the same component. So we cannot keep doing the process forever, because the first two restrictions says that we have to take 1 and we cannot take n. But if we do that, then we'll have to pick a subset like this. And if we pick a subset like this, then we are crossing some edges. And when we cross an edge, that means that we're taking some element from a restriction and not taking another element from a restriction. So that will limit our time for that will limit for how much time we can do this operation. So this is when we are not going to make an infinite number of, we're not going to play an infinite number of times. So here our goal is to maximize the number of times that we can play. So for this, at first, we're going to take all the nodes which are not n. So we're going to take all the nodes which are not n, and there might be some nodes like this. They do not concern us. We're not going to take them. We're just going to take all the nodes that are connected to 1 and that are connected to n. So we're going to take all these nodes. But now, for how much time can we do this? Can this subset occur? That restriction will be defined by these values. So for the edges that we cross, the restriction will be defined by them. So the minimum value among these edges, which is 2, this will define that we can take this subset and we can play with this subset for 2 units of time. If we play more than 2 units of time, then let's say for this edge, this one and this one, then we're playing with this for more than 2 units and we're not playing with this for more than 2 units. Then this restriction, this edge, will not be satisfied. So we can do this at most 2 times. So let's say we do this at most 2 times. So this was, yeah. So we do this at most 2 times. Now, for all these restrictions, their time will be decreased by 2. Because we already used up 2 for these edges. So we'll decrease 2 from them. So this will have 0, 1, this will have 0. Now, as this edge has 0 time, so we can think of this node similar to the nth node now, because we cannot cross this edge anymore. So we'll think this node similar to the nth node. So let's call these nodes bad. So at first, the 5th node was the only bad node. And now, as these 2 edges became 0, then these 2 nodes will also become bad nodes, because we cannot take them in our subset anymore. Because if we do that, we're going to cross these paths. So 3 and 4 will become bad nodes now. Bad 3 and bad 4. They will become 1. All the other nodes remain, let's say, good nodes. So again, for the nodes which are not bad, so these 3 are bad nodes. Now we can take these 2 nodes and these 2 nodes in a subset, and the edges will define how much time can we take this node, this subset, my bad. So the edges that we cross is going to define that we crossed this edge, we crossed all these edges now. So 2, 5, 1, and 5. So the minimum of them 1 is going to define it. So now the time from all these edges is going to be decreased by 1 again. And then we're going to keep repeating this process. Some nodes are going to turn bad. And for each of the steps, we're going to check for all the nodes which are reachable from 1. And we can take them in a subset. And after each step, we're going to keep increasing the bad nodes. And we'll do this as long as we can and add up the times. So at first, we added 2 to our time, then we'll add 1 to our time, and so on. So we need multiple DFSs here. So we will call DFSs as long as we can take subsets, and as long as all the nodes are not bad nodes. So any doubts? This might be a little hard to understand. I agree, but you guys can ask if you have any doubts.
Can you explain from the part when we make 3 as bad node?
Yeah, sure. So at first, 5 or the nth node was the only bad node, but when we take this subset, then we are using up these edges. We can only use up these edges for minimum of 2, 3, and 2 times. So do you understand up to here?
Yes.
We can only use this subset 2 times. So for all the edges that are connected to the bad nodes, which is 5, their capacity is going to be decreased by 2, right?
Okay.
And now, as this capacity is 0, then it is not possible to take 4 and not take 5. So we cannot do this, because if we do this, then this restriction gets violated, right? Does this make sense?
Yes.
So this is why we cannot take 4 in a subset. So now 4 will become exactly like 5. We'll consider this as a bad node, and we'll consider also 3 as a bad node. Okay.
Okay.
So now we can take 1 and 2 in a subset, and we'll check all their adjacent nodes, adjacent edges, sorry, and check their minimum value. And this is also going to denote how many times can we take this subset. Then we'll decrease the capacity of those edges, and we'll find new bad nodes. And we'll keep doing this as long as we get, as long as all the nodes aren't bad nodes.
After 3, one can become a bad node. So what will we do?
If 1 becomes a bad node, then we cannot do this anymore, because 1 has to be in the subset. Then we'll just break out. But let's say 2 becomes a bad node, then we just have 1 as a good node. Then we can also do this one more time. Afterwards, 1 will become a bad node, then we'll just break out.
Okay.
Okay, so let's take a look at the code. The code might be a little messy. I'll try to clean it up a little bit. Let's take out all the messy things. Yeah. After you're done with code, can you show the code for the second? Yeah, I'll show the code for the second problem. So this is the code. We're taking n and m in input. Then we're taking all the edges in input, and we'll store them in an adjacency list like normally. But we're also going to keep another value, which is the index. Okay, so let's explain it with an example. Let's say we got an edge like this, 1 and 5, and let's say time is 3. So this is u, v, and y. So in the adjacency list of 1, we're going to add 5 right now, 5, 3, this pair right now. And we're also going to include 1, 1 and 3 in the adjacency list of 5. But I'm also, but there might be some other values here, some other edges in this two adjacency list. So I'm going to include the index of this value. So let's say there are 2 values previously. So the index for this will be 2. I'll include the index for this value here, and I'll include the index for this here. So let's say there are 3 values previously. So the index of this will be 3. So I'll include this here. We will need this after. We'll need this later to do some operations. So at first, we'll mark node n as bad, and we'll run a DFS. So here in the DFS, this is the very first DFS, and we're going to use this to decide if 1 and n are in the same component or not. So in this DFS, if the node is visited, we'll return. Otherwise, we'll mark this node as visited, or we're going to go to the adjacent nodes of this node. And if some node is bad, so if we find node n at first, then we're going to take the minimum value of that edge. So the minimum mn variable is set to infinity at first. So if we find the node n, then this value will be updated. Otherwise, if the node is not visited, then we're going to visit that node. So after we're done with the DFS, if the main variable contains in, then that means we didn't reach n during our DFS. So we're going to print out infinity because 1 and n are in different components. But otherwise, 1 and n are going to be in the same component. So then we can we're going to need multiple DFSs. So here I have a variable answer. This will store the maximum amount of time that we can play. We also have a vector, and also we also have a vector of strings and longs. So this is for the output format. So the output format is like, yeah, the output format is like this. So we have to print out once for the elements that we pick in the current subset, and this is the amount of time that we can play in this subset. So these are these two vectors will store those values, and I'll take it now string, and for all the nodes that are visited now, we're going to add 1 to it. Otherwise, we're going to add 0. So we add these 2 values in the output vectors now. And in here, in this while loop, we're going to run our operations for as long as we can. So yeah. So after running this DFS, some nodes will turn bad now. So I have another array. I'm calling this new bad. So at first all the values are zeros, and I'm going to mark the new nodes that will become bad. So for all the nodes, if the current node is bad, we're going to check all the edges going out from this node. So we're going to decrease the value by mn, decrease the weight of that edge by mn, and here we're going to use that index. So the index that is stored here, we're going to use that index. So that is going to be this, to decrease the value. So let's say the age right now is from 1 to 5. So we're going to use that index to decrease the age from going from 5 to 1. So that is what we're doing here. And if the weight of this age becomes 0 or less now, it will not become less, it will become equal to 0. Then the new bed will be turned on. So new bed of this node will be 1 now. And after we're done, we're going to include the new bed nodes into the bed array. So we're just going to order all the values. So if 1 becomes bad, then we're going to break out. Otherwise, we're going to run another DFS. So at first, I'll mark all the nodes as not visited. We'll reset the mn variable to int. Then we'll run a DFS. And similarly, the current minimum cost that we get, sorry, that is going to be added to the answer. And again, we're going to calculate the now string, and we're going to add these two values to the vectors. Then finally, we can just print out the answers. So any confusions with the implementation? Any doubts? Okay, I guess not. So we are done with problem B, and someone asked to show the code for problem B, I think. So are you here? Who asked? Yeah. So let's take a look at the code for problem B one more time. So did you understand the approach that I described? Yeah, so then you should understand it. So we're taking the 3 arrays in input. Then for the 3 arrays, I'm going from top to bottom, and I'm checking if the current variable contains any bit that is 1 and in X that is not 1. So by doing that, now our X is not equal to X, we can check that. So if that is the case, we're going to break out. Otherwise, we're going to include this value to the total OR array or total OR value. Afterwards, if total is equal to X, then we're going to print yes, otherwise no. So is it clear now? Okay, great. So yeah, so this was the post contest discussion, guys. Thank you guys for attending.